So let's quickly go through what we covered in the last lecture in case you have not had a chance to look through the material. So as an application, as a very important application of the Frobenius method of solving differential equations, we consider Bessel's equation. So Bessel's equation is an equation of this form. Usually it's written in the form given as equation number 1 here. Of course, if you divide through by x squared, you can easily show that this satisfies the conditions for the Frobenius series to apply. So you try a solution of the form y of x is summation amx to the m plus r, where r is a parameter that you have to determine. And then you basically differentiate this and plug this back into the differential equation. And then you look at the lowest power of x in the ensuing differential equation, or rather ensuing algebraic equation, a power series for x. And you find that in this case, the indicial equation is r square minus nu square equals 0, which tells you that there is two solutions possible, r1 equals plus nu and r2 equals minus nu. At this stage, we do not make any assumptions about nu. It could be an integer, it could be anything, as long as it is some number greater than 0. So we do not know under what class of solutions this appears, right? So unless nu is equal to 0, we don't have a double root. That much is certain. Of course, for nu equal to 0, we do have a double root. But if nu is not equal to 0, and if r1 and r2 do not differ by an integer, we have two independent solutions. And if they differ by an integer, you could possibly have a logarithmic term in the second solution. So these are things that you already know. So then you look at the series for r equals nu, one of the two roots, and you derive the recursion relation, which we did. And it turned out that this equation is such that all the odd coefficients vanish and only the even coefficients survive. And we were able to derive a general form of these even coefficients in terms of course, the in terms of the first coefficient a0, and it turned out to have this particular form that is visible on the screen. Okay, so at this stage we kept nu arbitrary, and now we specialized to an integer nu. And if we specialize to an integer nu, we found that with a judicious choice of a0, you can clean up the denominator of this a to m quite gracefully, and the whole thing collapses into a factorial. Okay, so with the choice of a0 as 1 over n factorial, I'm able to collapse these unwieldy factors of n plus 1 times n plus 2 and so on and so forth into a neat n plus m factorial. And this enables me to write the solution, which I'm calling Jn of x. This is the Bessel's function of the first kind of order n in a neat form in this fashion. So look at the x to the n, and this is reminiscent of the x to the r out front and Frobenius method. Of course, r in this case was nu, and nu we have specialized to the case of integers n. Okay, in general, you would have an x to the nu here. This was the particular form that we got for an integer nu, and you can show by ratio test that this series converges, so there is absolutely no problem. Okay, now if to get an idea of how these guys look like, we evaluated the n equal to 0 and n equal to 1 Bessel functions, and we found that even though the coefficients were different, the j0 went like 1 minus x squared plus x to the 4th and so on and so forth, sort of like the cosine series. And the j1 went like x minus x cubed plus x to the 5 and so on and so forth, which looks like a sine series. So this enabled us to conclude that at least for these small n's and for large x's, these jn of x's can be approximated by sine and cosine. Okay, of course, they are not exactly sine and cosine. They, for example, their zeros are not equally separated and so on and so forth, but they have a neat form in this particular fashion. Okay, so having done all that, we now specialized to the case of an arbitrary nu, not necessarily an integer, something that is greater than or equal to 0, but not necessarily an integer. In this case, of course, we went back to the drawing board and we wrote down the recursion relation, of course, and a to m is given by the exact same expression. Of course, in this case, nu is not n. And we asked what we can do to a0, what choice of a0 would make our lives easy. So notice that formally we already have a solution. We don't have to do any of this in principle, but it turns out that in most practical applications, it is useful to have a series that looks a little compact. So you look for a particular choice of A0 that might make this series a little less unwieldy. So that is the motivation behind choosing a particular value of A0 here, which in this case turns out to be proportional to the gamma function. Okay, so we define what a gamma function is. In case you have not seen this, please go through this portion. And gamma function has this very nice property that gamma of nu plus 1 is just nu gamma nu. Okay, and this tells us that if nu is an integer, of course, you can keep going down the ladder this way, right? And I can write this gamma nu as nu minus 1, gamma nu minus 1, and so on and so forth. And I can figure out everything in terms of gamma 1. And this is reminiscent of the factorial. So the gamma function in this case is an extension of the notion of a factorial in the case of a non-integer nu. Okay, so we used this fact and then we found that the denominator again collapses in a nice form, not a factorial form, but a gamma function form. And a to m turned out to have this compact form. Okay, so minus 1 to the m, 2 to the 2m plus nu, m factorial times the gamma function of m plus nu plus 1. Okay, so if you specialize to the case of an integer nu, you get back the exact same form that we derived here. Where was that? Right here. Okay, so I leave that as a check for you to do. It's very straightforward. Okay, so this is where we stopped. So we then wrote down the Bessel function of the first kind of order nu, and I should explain why this is the first kind. We will do that today. And we have to basically continue at this point. And today the plan is to talk a little bit more about Bessel's functions. And I'll introduce why we need the notion of a Bessel function of a second kind, and then hopefully wrap up the discussion of Bessel functions. Before I begin today's lecture, are there any questions about any of the stuff that's already done on Bessel functions? So notice that everything that I've talked about in Bessel functions is a straightforward application of the Frobenius series. So if you simply plug in the series and do everything out, you should get exactly what we have derived here. Okay, so I'll take this as my starting point and we'll begin today's lecture. So I will start by writing j nu of x again, even though I have it right here. M equals 0 to infinity, 2 to the 2m plus nu m factorial minus 1 to the m x to the 2m. Okay, so this only has even powers of x. So as an example, to just like we looked at what the Bessel functions look like for n equal to 0 and n equal to 1, let us start by looking at a particular example. So example, it turns out that these functions have a particularly simple form for half integers. So let us evaluate what j half of x is. Okay. So let us put nu equal to half in this series and let us evaluate this explicitly as an example. So x to the nu, which is square root of x, m equals 0 to infinity, minus 1 to the m, 2 to the 2m, plus nu. Nu is a half, so I have a square root of 2, m factorial, 1 over gamma of m plus 1 plus a half, which is m plus 3 half, x to the 2m. Okay. Now I can multiply and divide this guy by x over root 2. The reason I do that will be apparent in a second. Okay. Now if I do this, of course, this is just 1, so I can always multiply and multiply by 1. And I should also, before proceeding, tell you that this gamma function can also be evaluated. So remember that gamma of nu plus 1, which is defined as the integral 0 to infinity e to the minus t, t to the nu dt, is actually equal to gamma nu times gamma of nu. Okay. So what is j half? So I can write this as square root of 2 over x on the outside, m equals 0 to infinity. There is nothing I can do to the minus 1 to the m or x to the 2m, so I'll keep them as such. So now notice that Since I've taken this square root of 2, so I'm taking this factor outside. Okay, so square root of 2 over x times square root of x becomes square root of 2 over x. Okay, so which means the factor x over root 2 remains inside. And now there is 2 factors of root 2 in the denominator. So this becomes 2m plus 1. M factorial remains, and this remains as gamma m plus 3/2. Okay. So let us look at this denominator. So I'll call this some d, and d I will write as 2 to the m factorial times 2 to the m plus 1 gamma m plus 3/2. I'll write this as these 2 separate factors. The reason is because this denominator actually has a very simple form. And to get to this simple form, we will write this denominator in 2 separate factors in this way. Okay. So remember that 2 to the m times 2 to the 2m, 2 to the m plus 1 is basically 2 to the 2m plus 1, and everything else is here. So I'm not missing any factors. So what is this guy? 2 to the m factorial is basically, I can write this as 2 times m times m minus 1, m minus 2, all the way till 2 times 1. Okay. Now I'll migrate each factor of this 2 to each factor of this factorial. So I'll call this 2m times 2m minus 2, 2m minus 4, so on and so forth, all the way till 4 times 2. This is the first part of the denominator. Okay. Now, admittedly, this looks a little more unwieldy than just writing it as 2 to the m times m factorial. But in 1 second, you will see that this whole thing collapses to something simpler. 2 to the m plus 1 gamma of m plus 3/2 can be written as 2 to the m plus 1. Remember that gamma nu plus 1 is nu gamma nu, right? So I can write this as, remember that gamma of m plus 3/2 is basically gamma of m plus 1/2 plus 1. Okay. So this can be written. So this would be equal to nu gamma nu, right? So this would be equal to m plus 1/2 gamma m plus 1/2. Okay. Again, this can be written as m plus 1/2 m minus 1/2 gamma of m minus 1/2, and I can keep going this way. So I can write this factor as m plus 1/2 m minus 1/2 m minus 3/2, and so on and so forth, all the way till 3/2 times 1/2, and the very last thing that I will end up with is gamma of 1/2. Okay. So again, I will migrate this factor of 2 to the m plus 1 into each one of these brackets, so that I have 2 to the m plus 1 gamma of m plus 3/2 is basically 2m plus 1, 2m minus 1, all the way till 3 times 1 times gamma of 1/2. Okay. Any questions or any comments about this? This manipulation is okay? So the only thing that remains to be done to evaluate j1/2 is to basically find out what gamma of 1/2 is, but gamma of 1/2 is actually a straightforward integral. Gamma of 1/2 is basically 0 to infinity e to the minus t, t to the minus half dt. Okay. Now if you put t as u square, you can evaluate this to be 0 to infinity e to the minus u square. Okay, t to the minus 1/2 is basically 1 over u, and dt is 2u du. So you can write this as 0 to infinity e to the minus u square du. You can convert this simply into a Gaussian integral. Have you guys seen Gaussian integrals before? Do you want me to evaluate this, or do you know how to evaluate this already? Yes or no? Okay. So I will assume that you guys know how to deal with Gaussian integrals. So you can basically square this integral and then go to polar coordinates and evaluate this guy. And you will actually find that gamma of 1/2 is square root of pi. Okay. So put everything together in the denominator. The denominator would become, so you will have factors. So from the first guy, you will have factors like 2m, 2m minus 2, all the way till 4 times 2. And from the second guy, you will have factors like 2m plus 1, 2m minus 1, all the way till 3 times 1 times square root of pi. Okay. So putting everything together, you would actually find the denominator to be 2m plus 1 factorial square root of pi. Okay. So after everything is said and done, it actually turns out to be something rather simple. So j1/2 of x would be square root of 2 over x, m equals 0 to infinity, minus 1 . Sorry, there is this factor of x in the numerator that I missed. So there should be 2m plus 1 here, right? So minus 1 to the m, x to the 2m plus 1 divided by square root of pi, 2m plus 1 factorial. And hopefully you recognize what this series is. This series is basically just a sine series. Okay, this is just minus 1 to the m times odd powers of x divided by the corresponding factorial. So this tells you that j1/2 of x has the very simple form. I'll just take the square root of pi outside. Okay, so that's rather neat. So just like j0 and j1 are related to the sine and cosine functions, but not exactly, the j1/2 and similarly we'll also find j minus 1/2 are related to the sine functions. Not exactly, there is a factor of 1 over square root of x out front, but a simple form for these guys can be found. Okay. So anyway, so now that you know what J nu is, right? So remember that going back to the integral equation, there was two independent solutions, one for r equals plus nu and one for r equals minus nu, right? So series solution of Bessel's equation is basically now given by J nu and J minus nu. Of course, we have to go through all these steps for R equals minus nu, but we don't need to do that because we know what J nu of X is, right? We just figured it out right here. X to the nu minus 1 to the m, x to the 2m, m factorial gamma of m plus nu plus 1. Okay. And to understand what the solution would be for for r equals minus nu, we could simply substitute nu to minus nu in this equation. So the other solution would be x to the minus nu, because nu appears as a squared in the Bessel's equation. The only change that will happen in all the recursion relations and so on and so forth is the substitution nu goes to minus nu. So I can do that with impunity at the last step. So m equals 0 to infinity, minus 1 to the m, x to the 2m divided by 2 to the 2m minus nu, m factorial gamma of m minus nu plus 1. Okay. So now the question is, are these two linearly independent? Well, it turns out that if nu is not an integer, if nu is not an integer, j nu and j minus nu are linearly independent. Okay, so if nu is not an integer, I can write the general solution to Bessel's equation as y of x equals c1 j nu plus c2 j minus nu. Okay, it's actually easy to see this cannot be linearly dependent because you have a factor of x to the nu in the j nu and x to the minus nu in j minus nu. Okay, so the if you divide one by the other, you would definitely not get a constant. Okay, but what happens if nu is an integer? What if nu is an integer? In that case, are Jn and J minus n linearly independent? Let's investigate. So let's put nu in this. Let us look at the formula for J minus 2 and let's put nu to be an n. So J minus n would be equal to x to the minus n, m equals 0 to infinity, divided by 2 to the 2m minus 1, m factorial. Okay, so notice that since now nu is an integer, this guy gamma of m minus n plus 1 is basically just m minus n factorial. Okay, so I can write this. I will also substitute m equals n plus s. In other words, I'm looking at the difference m minus n and calling this as some s. Okay, so rather just to make things a little easier, I will say m minus n is some s. Okay, I don't know what n is. Similarly, I don't know what s. So it's okay. So this becomes m equals 0 to infinity minus 1, or rather now I'm creating m for s. So I'll call this s is equal to 0 to infinity. M becomes n plus s. 2m becomes 2m minus n becomes what? 2m is basically 2s plus 2n. So 2m minus n becomes 2s plus n. 2s plus n divided by 2 to the, again, 2m minus n becomes 2s plus n. And m factorial would be just n plus s factorial. And gamma of m minus n plus 1, which is m minus n factorial, is just s factorial. And you see that if I pull out a factor of minus 1 to the n, this is and this is basically just j of n. Okay, so whatever remains here, if you look at this guy and substitute nu equal to n, you would get exactly this formula. So this is basically just minus 1 to the n jn of x. In other words, you find that if nu is an integer, jn and j minus n are not linearly independent, because if you divide one by the other, you just get a constant, which is minus 1 to the n. Okay, so if nu is an integer, jn and j minus n are not linearly, linearly independent. Which means now our job is to find a second linearly independent solution for the Bessel functions. Okay. So the question is, how does one go about constructing it? So that is what we would like to understand. Okay. So how to construct a second linearly independent solution. So let us begin at the beginning. Let's go back to the drawing board and let us write the Bessel's equation. Bessel's equation is x square y double prime plus x y prime plus x square minus nu square y equals 0. Okay, I'll first do it for, remember that I want it for nu equal to integer. So I will first start with nu equal to 0. Okay, that's the simplest integer that I can think of. So nu equal to 0, this becomes x square y double prime plus xy prime plus x square y equal to 0, or if I divide through by x, I get x y double prime plus y prime plus xy equal to 0. Okay, so again, I'll try a Frobenius method. I will try y, excuse me, I'll try y equals am x to the m plus r. Okay, now of course my integral equation would be such that I get two roots plus nu and minus nu, but since nu is equal to 0, my integral equation of course will give me double roots. Nu equals, sorry, not nu, r equals 0, 0. Okay, because in the general case, your integral equation is plus minus nu. Of course, for nu equal to 0, you would of course get a double root. So in the case of a double root, you know how to write down the second linearly independent solution. So let's call the first solution J0 of x. Okay, so this is y1. So our general rule in the case of a double root tells you that the second solution should have the form J0 of x logarithm x plus m equals 1 to infinity am x to the n. Okay, where these coefficients capital M are different from these coefficients little a. Okay, now I also want to alert you to one typo in the notes. This for the double root case, the second solution should be such that this series goes from m equal to 1 to infinity. There is no a0 term, okay, in this. So this is, I think, a mistake I made when I wrote down this for the first time. So when I go back to the Frobenius series introduction, so when I wrote down the double root case, so I didn't erase this because I wanted you to realize this. I wrote here m equals 0 to infinity. This is a mistake. So this has to be m equals 1 to infinity. Okay, so please do make this correction in your notes also. Okay. So now coming back to this. So what I want to do is, I know how to basically figure out J0 because that's something that I've already done. I need to figure out what Y2 is. Okay, so to figure out what Y2 is, I basically have to figure out what these coefficients capital M are. So basically the idea is to plug in this onsorts into the differential equation and figure out a recursion relation for capital M. So what is Y2 prime? Y2 prime would be J0 prime logarithm x plus differentiate the logarithm, you get J0 over x, and differentiate this guy, you get m am x to the m minus 1. Y2 double prime would be J0 double prime logarithm x plus J0 prime divided by x. Now I have to differentiate J0 over x. So I'll first differentiate J0 and then I'll differentiate x. So I get J0 prime over x if I differentiate J0, and then I have to differentiate 1 over x. So this gives me minus J0 over x squared plus m equals 1 to infinity m minus 1 am x to the m minus 2. Okay, so I can clean this up and write this as J0 double prime log x plus 2 J0 prime over x plus m minus 1 am x to the m minus 2. So for completeness sake, I'll also write y2 here, which is J0 log x plus m equals 1 to infinity am x to the m. So I have to substitute all of these guys in the Bessel's equation. So what's the Bessel equation in this case? Xy double prime plus y prime plus xy equal to 0. So let's do that. So look at y2 double prime. If I multiply this guy by x, I get x j0 double prime log x plus 2j0 prime. The 1 over x cancels the x minus j0 over x plus, since I'm multiplying by one factor of x, the x to the m minus 2 becomes x to the m minus 1. Okay, so that is the xy double prime term. The y prime term I will write as such. So the y prime term would be j0 prime log x plus j0 over x plus m equals 1 to infinity. And now the last term is x times y. So that would be x j0 log x plus m equals 1 to infinity am. There is a factor of x. There is a factor of x to the m. So this is x to the m plus 1. This whole thing has to be equal to 0. So remember that my assumption is that j0 is the first linearly independent solution, which means if I add this plus this plus this, I get 0. Because j0 is a solution of this equation. So if we substitute y equal to j0, I get logarithm x times xj0 double prime plus j0 prime plus xj0. So these three terms sum to 0 because j0 is a solution. So these three terms sum to 0 because j0 is a solution. Moreover, the plus j0 of x here cancels the minus j0 of x. Okay, so put everything that is remaining. I get the 2j0 prime plus am m minus 1 x to the m minus 1 plus am x to the m minus 1 from the y prime term plus am x to the m plus 1. This whole thing has to be equal to 0, and this simplifies further because the minus m from this guy and the plus m from this term completely cancel because the coefficients are the same. They are both coefficients of x to the m minus 1. So this implies that 2j0 prime plus am m square x to the m minus 1 am x to the m plus 1 equals 0. Okay, so this is the equation that you obtain. Of course, you already know what j0 is, which means you already know what j0 prime is. So you know jn of x to be x to the n minus 1 to the m x to the 2m divided by m factorial n plus m factorial, right? So which means if I put n equal to 0, I know j0 is minus 1 to the m x to the 2m divided by 2 to the 2m m factorial whole square because n is 0. So j0 prime of x would be minus 1 to the m So if I differentiate x to the 2m, I bring down a factor of 2m, which cancels one factor of 2m below. So I get x to the 2m minus 1 divided by 2 to the 2m. So I'll write this explicitly, 2m, 2 to the 2m, m factorial whole square. Okay. So you can show that one factor of 2 cancels one factor of 2 here, and one factor of m cancels this m factorial whole square. So putting everything together, you would find that this series can be written as m equals 1 to infinity So I take this factor of 2 and take off one factor of 2 from the bottom. Then one factor of m makes one of these m factorials m minus 1 factorial. That is the j0 prime. Oh, by the way, there is also a 2 here, okay, because it is 2j0 prime. So that factor of 2 basically makes this 2 to the 2m minus 2. Okay, so please check the algebra properly. I'm sure you will get this right. And this becomes m equals 1 to infinity m squared am x to the m minus 1 plus m equals 1 to infinity am x to the m plus 1 equals 0. Okay. Now, if you look at this equation, notice that everything starts at m equals 1. And if you put m equals 1 in this series, you find that only this guy has a coefficient x to the 0, the constant term. Okay, so remember that if this has to be a valid series, term by term, the coefficients of x should vanish, right? So if you put m equals 1, the first term, so m equals 1, the first term gives me x, right? Because 2 minus 1 is just 1. So the first term gives me x. The second term gives me x squared. And it's only one of these terms that gives me x0. So if I equate the coefficient of x0, I find a1 to be equal to 0. Okay. So similarly, you can show that all the odd coefficients vanish, and I leave it as an exercise to show that the even coefficients a to m can be written as minus 1 to the m minus 1, 2 to the 2m m factorial whole square times the series 1 plus 1 half plus 1/3 plus 1 over. Okay, so this is straightforward to show from this series expansion. Okay. Now one could always, so basically we are done. So once we know what the coefficients are, we can construct the second linearly independent solution y2, because y2 is basically j0 times logarithm x plus some am x to the n. So once we know what ams are, we know what the series is. Okay. Sometimes in the literature, you also see this as in a different basis. If we choose a different basis, right, and you can write this as a times y2 plus bj0. So remember that j0 and y2 are linearly independent solutions by construction, because y2 is the linearly independent solution for the n equal to 0 case. I'm not doing the general n case. For n equal to 0, at least we have figured out that y2 is a linearly independent solution because you get a double root and so on and so forth. Okay, so conventionally, people choose the second linearly independent solution in this form, a times y2 plus bj0, and a is chosen to be 2 over pi, and b is chosen to be gamma minus log 2, where this gamma is 0.577. It's called the Euler-Mascheroni constant. Euler constant. Okay, so putting everything together, you can write down the second linearly independent solution for the n equal to 0 case. Second linearly independent solution for the n equal to 0 case, and this is given by y0 of x. J0 of x logarithm x by 2 plus gamma plus m equals 1 to infinity m minus 1 hm divided by 2 to the 2m m factorial. This is basically a to m times x to the 2m, where instead of writing this series over and over again, I've called this some hm. Okay, hm is basically 1 plus 1/2 plus all the way to 1 over 2. Okay, so the two linearly independent solutions in the case of the n equal to 0 Bessel's equation are J0 and Y0, and this is called Bessel function of the second kind of order 0. Okay, this is also called the Neumann function of order 0, and this is denoted not by J0 but by Y0, because this is a different solution than the J0. Now, how do you tackle n equal to 1, n equal to 2, and so on and so forth? Well, in principle, you can go through the entire thing again, right? So I can write things for n equal to 1. I can start with the Bessel's equation for n equal to 1. I can again write down the Frobenius expansion, and I will write down the integral equation. Of course, in this case, the integral equation will not be 0, 0. It will be plus minus 1. The roots are plus minus 1. So I will write, and plus minus 1, of course, differs by an integer. So I will write down the general solution for an integer for two integers, and the difference between the two is also an integer. So I will write down the solution that is pertaining to that particular case, and I will using that particular onsorts, which is basically some k times J0 logarithm x plus some m equal to 0 to infinity amx to the m. Again, I will go through the exact same thing. I'll demand that this y2 satisfies the Bessel equation, and then I will use this to figure out the recursion relations and find the series for n equal to 1. Of course, this is very laborious to do, and it is not a very practical way of doing things out. For each n, we have to go through this method again and again. So there is a convenient general solution available, and the general solution, which I will not derive but just give to you, is this. General solution of the Bessel's equation, excuse me. To do this, of course, I need two linearly independent solutions. The second solution, the general form of the second solution, is given by y nu of x equals 1 over sine nu pi divided by j nu of x cosine nu pi minus j minus nu of x. Okay. Now you might wonder why we are writing it for nu, because for a non-integer, we already know two linearly independent solutions of the Bessel's equation. That is j nu and j minus nu. So basically, I'm writing the second solution as some linear combination of j nu and j minus nu. So by construction, this y nu and j nu are linearly independent. Y nu and j nu are linearly independent because y nu is defined with respect to j minus nu, and we already know that j minus nu and j nu are linearly independent. Okay, so there is absolutely no problem in constructing this solution for a non-integer, because I'm simply taking one linear combination of the solutions, and that is also a solution. Okay, so there is absolutely no problem in the case of a non-integer. In the case of an integer, yn of x, I simply have to take the limit nu goes to n of y nu of x. Okay. Now, on the face of it, this looks like this limit might not exist because it is a singular limit. Because if I take nu to be an integer, 1 over sine n pi basically is 1 over 0. But you can actually show that for any x greater than 0, this limit actually exists. Okay. So we will not do this out, but we will simply leave it at this, and we will claim that this limit exists. And in the general case, I can always write the solution y of x of the Bessel's equation, the general solution, as C1 j nu of x plus C2 y nu of x, where j nu and y nu are already derived for you. J nu is already derived and y nu is given to be this particular form. Okay. So this is how we approach the Bessel's equation. Admittedly, it is slightly more complex than the Legendre equation, which for which the solution was rather straightforward. We never had to worry about how to find a second linearly independent solution because there was no subtleties involved. But in the case of Bessel's equation, there is a little bit of subtlety depending on the integral equation and whether nu is an integer or not an integer, and so on and so forth. And you have to be a little careful if you're solving a particular problem in the Bessel's equation, because you have to look at the solution carefully and see if it is for an integer or not an integer. Of course, the advantage of this formula, this second solution y nu, is that it is applicable for both integers and non-integers. So if you want to specialize this to an integer, simply substitute nu equal to n and take the limit carefully. That's it. Okay. So this is the general methodology in applying the Frobenius method to the case of Bessel's equation. Okay. So we'll stop here at this point.